last week, exactly 1 week ago actually, we discussed a lot of things in Euclidean space. And we discussed a lot of concepts. We discussed the different types of basis vectors we have in Euclidean space and different types of coordinate systems that we can have in Euclidean space. And the reason we did that was that many of the concepts we will encounter in calculus and manifolds, or differential geometry as it's called, which is the language that we will use to describe general relativity, they remind very much of what we did last time in Euclidean space. So what we did last time was kind of a preview for what we're going to do today. And also, let me say that we're going to spend 2 more lectures after this one, just going through the basic mathematics of how we will describe general relativity, which is the general framework of how we describe curved spaces. So what we're going to talk about today, at least the first lecture, or sorry, the first hour, is something that's called manifolds. Now, that's a fancy word for something that you will be more or less familiar with, at least. You already know several examples of manifolds. So let me just write down a few examples. So, for example, we have the circle, S1. That's a manifold. We have the sphere. Oops, if I can draw a sphere properly. So the sphere S2, that's a manifold. And also if I try to draw here something that kind of looks like a torus. Well, it is a torus, it's supposed to be a torus, which is essentially this donut shape, the surface of that's also a manifold. So all of these are examples of manifold. And if we want to be a bit more formal, so we can say that a manifold, that's a space, or rather let me insert here a n-dimensional manifold. It's a space that locally looks like a subset to Rn. So what does this mean? Well, it means that if I just look at the small part of the sphere or the circle, that should basically look like I am in R1 or R2 respectively. So if I look at the small area here on the sphere, like that, there should be a mapping from this small part of the sphere to a subset of R2 that is a smooth bijection, so that is invertible. So to put that down, so this means that a manifold should be described by a number of open sets so, or let me put in an M here. So let's call the manifold M. There should be a number of open sets Mi with a corresponding smooth function which I will call phi I, that should go from Mi to Ui, where Ui is a open subset of Rn. And this should be a bijection. And phi is a bijection. And this subindex I here just enumerates these different sets that should in total cover the entire space that we want to describe. So a construction like this is called a chart. So just like, I mean, it's not difficult to understand where this nomenclature comes from. A chart, if you look in a book of maps, that's essentially a chart, right? And if you look at the Earth as a sphere, a chart describes a small part of the Earth that locally you have mapped it to this flat two-dimensional map. So, for example, if we have this small part here, I can open an atlas, and I can find on one page there might be a chart describing precisely this patch of the sphere, or of the Earth in that case. So in order to have a complete description of a manifold, we need to ensure that each point on the manifold is described by at least one chart. So in order to have a complete description of M, for each point in M, each point P in M, there must exist an index I such that P belongs to this set Mi. That's just saying that the union of all these sets Mi should form the entire manifold. So in the case of the sphere, for example, it's not enough just to have a single chart. You need many charts in order to describe the sphere. So if this is so if we have such a collection of charts, such a collection of charts is called an atlas. And again, it's not strange to see where this nomenclature comes from. The atlas is complete if for every point on the Earth there exists at least one chart where that describes that shows you where that point is. So for example, if you're in Stockholm, in order for the atlas to be complete, Stockholm must exist in at least one of the charts that is in that atlas. So the component, and just the last thing here, if we have these functions phi I, that's a function that maps a point in a manifold to a set of n numbers, and it's actually those numbers, so the individual components of phi I are the coordinates of a point. So just as we discussed last time, in order to uniquely describe a point, if we have a coordinate system, then if we take all of those components and specify them, that will correspond to a point in the manifold, in particular in this set Mi. And we will denote them just as we did last time, by chi-a in general. And of course, if we have a particular set of coordinates, then we will use the standard naming conventions. So just a quick example regarding that is if we take the sphere that we have used, or that I already drew, see if I can draw it again. So if we take this sphere here, I mean, you're familiar with spherical coordinates in Euclidean space already. So getting a sphere in Euclidean space which is a subset then of Euclidean space, a two-dimensional subset, is just that we set the r coordinate to be constant. So we can let, for example, r be equal to r0, and then we can use the angular coordinates theta and phi are then coordinates on this sphere S2. However, in order for this to be invertible, to be a bijection, we will only be able to describe part of the sphere. For example, the poles are going to be a problem as our coordinates will be singular there. And also, in order for this to be a bijection everywhere where it's defined, we need to take out essentially a line that goes between the poles. So we restrict our coordinates theta and phi here. Theta we restrict to be between 0 and pi, and phi we can restrict to be between 0 and 2 pi. So this is going to describe everything on this sphere that I have not drawn in red here. So this is a chart which describes most of the sphere, but in order to have a complete atlas, we would also require some coordinate system or some chart that would describe also this part. So let me also say what the point of doing all of this is. So a sphere, I could of course go on and try to describe this sphere as a subset of three-dimensional Euclidean space. However, in general, this is not what we are going to want to do. Instead, what we will want to do is to describe the sphere only with things that are intrinsic to the sphere. So only using the coordinates of the sphere itself and not any reference to this three-dimensional space that is embedding the sphere. So our aim is to use only the properties of the sphere itself in order to describe geometry on the sphere. And as you might be familiar with, the geometry on the sphere is quite different from Euclidean geometry. For example, if I take a different color here and I draw a triangle on the sphere, so let me draw this triangle. This is essentially a triangle of great circles. The angular sum of these angles is not going to add up to 180 degrees. So in this case, alpha plus beta plus gamma is going to be greater than pi half in general. So the geometry of the sphere is going to be intrinsically different from Euclidean space, and essentially is what's going to be described by what we will discuss now. Also note that there is no in a manifold in general, such as this sphere or the circle or the torus. They are in general not going to be affine spaces. If we remember what we talked about last time, an affine space is somewhere where you can define an origin, and then you define a translation vector as the position vector, and that would uniquely describe a point in that space. In the case of the sphere, we don't have that possibility because it's not clear. If I take a point here, on the sphere, it's not clear what it would mean if I have a translation vector, say, along the sphere in some of these directions, along the tangent space of the sphere. What would that mean? Where would I end up? If I see it as a vector in three-dimensional space, I will certainly not end up on the sphere itself. So a manifold is in general not going to be in a affine space, which is going to mean that we will not have access to the position vector. And this poses a problem for the way that we in general tried to describe vectors, or try to find these bases of vectors in Euclidean space, because if we look at tangent vectors, so last time we defined this set of tangent of the tangent bases EA. We defined that as the derivative of the position vector with respect to the coordinate chi a. Now the problem we have here is that there is no position vector. So this generally does not exist. In a manifold. So we need to do something else in order to define vectors. And as it turns out, the way of solving this is just to remove this position vector. We will see that there is it was actually not necessary when we defined vectors to actually include this position vector, but let me discuss a little bit why. So the point, if you look back to Euclidean space, what is the point of having these vectors? Well, one point of using vectors. So one point of using vectors, or in particular translation vectors, is to look at how functions change. So you will remember that if we look at the directional derivative, so of a function f, we could write that as, well, in the direction of some vector v, we could write this directional derivative as the inner product of v and the gradient of f. But if we expand this in terms of the coordinates, this is just VA dA acting on f. So this means that this directional derivative here depends on the components of this vector v in this coordinate system. But this is rather interesting because it means that there is going to be a bijection between translation vectors such as v and directional derivatives. So in this case then VA dA. So what we are going to do is that since this bijection exists in Euclidean space, but we don't really have a handle on what vectors in Euclidean space mean, we're going to take vectors to be exactly those directional derivatives. So tangent vectors on a manifold are directional derivatives. And of course, then we have a basis for these directional derivatives, which are the partial derivatives with respect to the coordinates. So I'm going to write that just as dA, which is the partial derivative with respect to the coordinate chi a. So those are going to act as our tangent vector basis. So just to make this more plausible, let's consider how. Well, I'm also going to write this sometimes just as we did before as EA. So to make it more plausible, let's check how this would change if we check a different coordinate system. So for a different coordinate system, so let's use primes to denote that coordinate system. We have E prime A prime. That would be by definition, let me write it explicitly as d chi prime A prime. So it would be the partial derivative with respect to the prime coordinates. But then we could use the chain rule for derivatives and write this as d chi A d chi prime A prime times d chi A, or if we want to express it explicitly in terms of this E, d chi A d chi prime A prime EA. So we see that this is exactly the same transformation rule that we had for the basis vectors in Euclidean space. And of course, this comes from the fact that this position vector was not really important for the transformation rule. The only thing that was important for the transformation rule was the partial derivative itself. Any questions there? Okay, so we're calling this tangent vectors now. And if you remember what we talked about last time, we were talking about also tangent vectors of different curves. And so let's write that, tangent vectors of curves. So that essentially is, or was it, if you take a curve like this, gamma, then in some point here, we're going to have a tangent vector in Euclidean space. And we define that tangent vector. So I'm going to call this gamma dot now. We define gamma dot in Euclidean space as the derivative of the position vector with respect to the curve parameter S. So we would have a curve parameter S here that would parameterize the curve. Now this was, of course, if we use the chain rule here, this is the same as d chi A, d chi A ds multiplied by dx d chi A. So if we denote the derivative with respect to S with a dot, this would be chi dot A, and then this basis vector EA. And so how do we relate this to a directional derivative? Well, if we have a function f here defined in this space, so we have some function f of p that's defined essentially, well, it's defined on every point in this space. We would define now gamma dot should be a directional derivative. So that acting on f would be nothing else than how f changes with the curve parameter. It would be df ds. So if we look at what this is, again, the same mathematics applies. It's just that we've changed the position vector x for the function f. So this would, in the same manner, it would be chi dot a dA acting on f. So we see that this is indeed a directional derivative of the function f with components chi dot a. So it's the same components as we found for the tangent vector in Euclidean space. Right. So that's also one way of actually defining vectors in a manifold, is to define them as in terms of tangents to the coordinate lines in the same way. Any questions? Okay. So this, what we talked about now, let's see, I didn't say that, no. So these directional derivatives, so the set of directional derivatives at the point P, so P is a point in the manifold, we will refer to the set of all possible directional derivatives as this point is referred to as the tangent space of the manifold M at P. And we are going to denote this TPM. So the tangent space, T stands for tangent space, P denotes which point we're at, and M denotes that it's the tangent space of this manifold at the point P. Okay. So before we take a break, I also want to discuss what is, because if you remember last time, we were talking both about the tangent vector basis, but we were also talking about the dual vector basis. So the tangent vector basis had these indices downstairs and components with indices upstairs. But we also introduced a different basis, which was the dual basis. So in Euclidean space, we defined a dual vector basis. We called it EA as the gradients of the coordinate functions. Now the problem here, of course, is that we have not really encountered something that is like a gradient yet in a manifold. So the question is how we are going to define this dual vector basis in the manifold. So in general, if we have a vector space, so given a vector space V, we can define its dual. So its dual, and that is denoted by V star. That's the set of linear maps from V to real numbers. So this means that if we have a vector in any vector space V, an element of its dual space, V star, is going to map that any vector in V to a real number. And this is going to be true also for the tangent space. So the tangent space here is a vector space because you can add directional derivatives, and that's just the same thing as adding the vectors and taking the derivative in the summed direction, or you can multiply them by numbers. It's just going faster. So the dual space to this tangent space that we define, to TPM, is TP star M. So that's if I give you a tangent vector and I have an element of this T star PM, then it's going to give you a real number. And what we're looking for now is a way of constructing this, of finding a basis for this dual space. And we're going to see that it kind of corresponds pretty neatly to what we did here. So first of all, let us find one element of this dual space to make it more, I mean, the dual space now we've just defined as this abstract thing, which is the set of linear maps from the tangent space to real numbers. So what we can do then is let's take a function, f on this manifold M. So that associates to each point in the manifold, it associates a real number. We can then define the differential of f is an element of this dual space. And the way we will define it is that we define df, the differential of f, acting on a vector x. So if this df is going to be an element of the dual space, it needs to take a vector as an argument. But we define this to be the derivative, rather this vector field x, acting on the function f. So that's the same thing as we had before. This is going to be xa dA f. So here x is an element of the tangent space itself. So it's a tangent vector. Now we can check that this is actually linear in the vector x, because if we take, for example, the f x plus y, this is going to be xa plus ya dAf, which is just xa dAf plus ya dAf. So it's indeed linear in the argument. So it is indeed an element of this dual space. So what we are going to do is that we're going to use this for the coordinate functions. So using this for the coordinate functions, which were chi a, we get that the differential of d chi a acting on a vector x, well, let's expand x in terms of the tangent vector basis. So that's going to be d chi a xb db. However, this d chi a is linear, so we can move this xb outside, and we're left with d chi a db. Now we just need to decode what this is. So d chi a db by definition was d chi a. Sorry, there needs to be a differential. It's d chi a. Oops. D chi a d chi b. So it's the differential of the coordinate function chi a with respect to the coordinate functions chi b. So chi a changes when chi b changes only if a is equal to b, and otherwise it doesn't. So this is nothing else than the Kronecker delta. So it's 1 if a is equal to b and 0 otherwise. So this is equal to xa in the end when we make the sum over b. So in particular, we see here that these d chi a's are they belong to this dual space dp star m. Not only do they belong to this dual space, but also they form a complete basis of this dual space. And we set EA equal to d chi a. And note here how similar this expression is with the differential of d chi a to this expression that we had up here, where the dual vector or the dual basis was defined by a derivative of the coordinate functions. In this case, we have a differential of the coordinate function that forms the basis for this dual space. So in general, any dual vector, I'm going to denote that by omega now. So it's an element of TP star M, may be expressed in terms of these differentials of the coordinate functions. So in particular, if I have this omega, it's a function of a vector, so omega x. This is equal to, in the same way as we've done before, let's expand this, xa dA, which is equal to, since it's linear, xa omega dA. And this thing here is what we would call the component omega a. So omega in this case would be written as omega a d chi a. And that would give exactly this expression for omega acting on x. So xa omega a. We can see this if we insert this expression here, we can see that also. So if we take omega of x, it would be omega a d chi a acting on x, and we have already seen that this is omega a xa. That's just using what we had here. So just before we take the break, I want to emphasize one thing here, and that's that while in the Euclidean space, the tangent vectors and the dual vectors belong to the same vector space. This is no longer true here, because in the Euclidean space, well, we had these directions already defined in terms of the position vector. But here we don't. So here a priori, the tangent space and the dual space are different. And in a pictorial way, you might view tangent vectors as arrows. So this is a tangent vector. Whereas a dual vector would be more akin to level curves. So this would be a dual vector. It tells you how something changes. For example, this differential tells you how the function f would change. And it does not a priori make sense to talk about the inner product in the tangent space unless you introduce an inner product. However, it will always make sense to talk about objects like this. So taking a tangent vector and a dual vector and mapping that to a real number. Now, in Riemannian geometry, so the geometry of curved subspaces essentially of Euclidean space, and in general relativity, we're going to have something that's called a metric, which essentially is going to define an inner product for us. But in the general setting, which might be applicable to something like thermodynamics, this will not be the case. So it's 2 o'clock. Are there any questions before we take a break? So actually, let me stop the recording for now. So another thing that we talked about last time were tensors on Euclidean space. So we will also deal, of course, with tensors in the general setting on a manifold. And now that we have defined the dual space and the tangent space, the definition of tensors, if we have access to this tensor product that we discussed in terms of the Euclidean space, is rather straightforward actually. So it's defined similarly to how it's defined in Euclidean space, to what we discussed for Euclidean space. So a NM tensor we define as a multilinear map taking n dual vectors and m vectors to a real number r. And we can define a basis of these NM vectors NM tensors as follows. We define these basis elements as A1 through AM. So one index per m, and B1 through Bn, so n indices. We define that as the tensor product. So I'm going to write this notation now. This a big O times with a index k running from 1 to m. So of the dual basis chi a k. So if I just wrote this out, this would be the chi a1 tensor product, and then all the way up to the chi a m. And then that times the tensor product of, let's use L now, from 1 to n, of these dB Ls. So the tensor product of the basis of the tangent vector space n times. So this thing here would be dB1 tensor product all the way up to dBn. So the point here being that each of these dchi's are an element of the dual space. So when you insert a vector in that, it gives you a number. So the first vector argument would go into dchi A1 here, and the last vector argument would go, the mth vector argument would go to dchi AM. And the corresponding thing for the dual space, that the first argument would go into, the first dual vector argument would go into dB1, and the last one would go into dBn here. So this indeed is an object that takes n vectors, n tangent vectors, and m dual vectors as arguments, and maps that to a real number. And any nm tensor here may be written as a linear combination of these basis tensors. So any nm tensor T may then be written T equal to T A1 through AM, B1 through Bn, multiplied by this basis. So E A1 through AM, B1 through Bn. And again, here we have the Einstein summation convention, so all of the indices are summed over. So this is a linear combination of all of these basis tensors. So that's how we define tensors in the general manifold. Once we have these objects, which are the basis of the tangent space and the basis of the dual space, we can construct the basis of arbitrary nm tensors, just using this to make a tensor product of those. Okay, so let's switch gears a little bit, and we're now going to discuss something that's going to become important when we start talking about derivatives of vectors and tensors in general on manifolds. So it's has to do with how we deal with functions on between manifolds, or a function from a manifold to itself. So what we're going to discuss is called push forwards and pullbacks. So the first thing with push forwards and pullbacks is that they relate to when you have a function or a mapping from one manifold to another manifold, or a mapping from a manifold to itself. So assume now we have a function or a mapping f between two manifolds, so from M1 to M2. Someone doesn't have their mic muted. Thank you. So that means that I have two manifolds. In general, I don't know how they look like, so this might be some subset of R3. We have another manifold over here. We don't know how that looks like either, but the point is that if we take a point P in M1, then that maps to some other point f of P in M2. So this is the basic setup. Now, M1 and M2 could also be the same manifold. It doesn't really matter for what we are going to discuss. And suppose now that we have a function g that is a function on M2. So it takes a point in M2 and maps that to a real number. Now, if we have this function f that we talked about, then any such function g is going to define a function also on M1, simply by composition. So this is going to define a function on M2, on M1, which we're going to call the pullback of g to M1 by this function f. And we're going to denote this by f and then a superindex star or acting on g. And it's going to be defined as the composition of f and g. So g composition f. So if we have if we take this point P here, we can map that to M2, which is done by the function f, and then we take the value of g at that point and define that as the value of f of the pullback of g. So in effect, f star g, that's a function on M1. So it takes p as an argument. And this is, in essence, the value of the function g in f of p. So this is now, so f star g, that's a function from M1 to real numbers. So just an example of that, a rather nice example. So let's look at the sphere. So look at the sphere. The unit sphere. So we take a sphere of radius 1 embedded in three-dimensional Euclidean space. Now, in three-dimensional Euclidean space, let's take a function on three-dimensional Euclidean space to real numbers. And one such function, it would be just that we map x, the position vector, to the Cartesian coordinate z. So that's a function. It's the coordinate function z. Now, if we consider standard coordinates, that's on the sphere, the composition, so these are the coordinates phi and theta, the composition of g and f, so the function f is a mapping from the sphere to R3, and it would just be given by, since it's the unit sphere, this would be sine theta cosine phi sine theta, sine phi, and then cosine theta. So the composition here, since g here, this is g of x, is picking out the Euclidean z coordinate, that would just be picking out this element. So this means that if we take here f star g, this should be a function from the sphere to real numbers. So it should take the spherical coordinates phi and theta as arguments, and we see that indeed what we get out of this is just cosine theta. So indeed it would be a function on the sphere that would essentially just be picking out the z coordinate on the sphere. So that about pullbacks of functions. So the terminology pullback here comes, of course, from the fact that we had a function over here on M2, and this function f here went from M1 to M2, and the terminology pullback means that we pull this function g that we had defined on M2 in the opposite direction of f. So we pull g from M2 to M1. So the next thing I want to discuss is called the push forward of tangent vectors. So as you can imagine, if the pullback is that we take some object here, which was a function in the example we saw, and pull it against the direction of f, a push forward is that when we have something defined on M1, such as a tangent vector, and then push it in the same direction as f to something that's defined on M2. That's exactly what we're going to do now. So the push forward of a tangent vector, well, let me copy these drawings here just to have the same. What we had here were two no, that I still want to keep. What we had here was a map from M1 to M2. And let's now consider the case when I have a tangent vector here in the point P. So let me call this V. That's a tangent vector in the manifold M1 at the point P. This is an element of T PM1. Now, as a tangent vector, it could be the tangent vector of a curve. So there's going to exist some curve in M1 that has this vector V as its tangent vector. Now, so let me call this curve gamma 1. Now, if I have this curve gamma 1, that's going to correspond, since this point P here corresponds to the point F of P in M2, this curve gamma 1, well, it's a set of points on M1, so I can map those points to M2, which will give me a curve. I don't a priori know what it's going to look like, but it might look something like this. So this would be gamma 2. So I would get gamma 2 by mapping the curve gamma 1 using the function f to M2. But this curve gamma 2 also has a tangent. And that tangent we're going to have here. That is what we're going to define as the push forward of V. Okay, so I will have to refill the battery of the pen. So the question is then, how can we describe this mathematically? The concept itself is just that we have a curve in M1 that corresponds to a curve in M2, and we define the push forward of the tangent vector in M1 as the tangent vector of gamma 2 in M2. If we look at it, the push forward here of V, we're going to define it as, we're going to call it F subindex star V. That should be a vector on M2, which means that it should be a directional derivative on M2. And that means that if we let this directional derivative act on some function, so we had this function g, for example, before, we take g from M2 to real numbers, then we define that F star V, the push forward of V, acting on this function g, is by definition the vector V, which was a vector in M1, acting on the pullback of G to M1. So just to make sure that things make sense here, this F star V, that's a vector on M2, and it acts on a function on M2. Whereas on the right-hand side here, we have V, which is a vector in M1, and that should be acting on a function in M1. And indeed, this pullback of G to M1 is a function on M1. But the more intuitive way of looking at this is what I described before, that we have a tangent vector of the curve gamma 1, and that maps to the tangent vector of the curve gamma 2 in M2. So that about vectors. Now you can do a similar thing if you have a n0 tensor. You just pull back the individual vectors. Oh, sorry, you push forward the individual vectors, or the individual vector bases too, and then you can make a push forward of an n0 tensor. What you can also do is, so we can push tangent vectors forward from M1 to M2, but we can also pull back dual vectors. So while tangent vectors can be pushed forward, dual vectors may be pulled back. So that is to say, if we have a dual vector in M2, then that is going to correspond to a dual vector in M1. We can pull that dual vector from this point to that point. And the idea is exactly the same. So if we take omega as an element of T f of P in M2, then that should be, then we define the pullback, which would be F star omega, an element in TP M1. We define that as F star of omega, F star omega. That should be now a dual vector on M1, which means that it should take a vector V, where this V is an element of TP M1, and map that to a real number. And the way of doing this is that we define this as omega acting on the push forward of V. it's similar to the definition that we had here of defining the pullback of, the push forward of V in terms of the pullback of F, but now going in the other direction. So here we have a dual vector on M1, taking a tangent vector on M1 as the argument, and that is by definition equal to this omega which we had, which was the dual vector on M2, taking this tangent vector on M2 as its argument. And you can, of course, you can extend this to 0 M tensors just by push forwarding all of the arguments. So for 0 M tensors, we can push forward all of the arguments. So so in that case, let's say that we have W, and it takes a number of arguments. That's a 0 M tensor on M2. We can define the pullback of W to M1, taking vectors V1, tangent vectors V1 through Vm as arguments, and that's then just defined as W acting on the push forward of all of those vectors. And finally, if we have mixed tensors, so we have tensors that are NM tensors, it's not generally possible to do a relationship between the two. However, so assuming F is a bijection, so that is F is going to be invertible, so exists an inverse of F, then we're going to be able to relate NM tensors on M1 and M2. So let's take an NM tensor T. That's then going to take T on M2. That's going to take M vectors and N dual vectors on M2 as arguments. So that would mean that we want to pull this back to M1, which means that it's going to take to Vm tensors, vectors, tangent vectors on M1 as arguments, and also a number of dual vectors, omega 1 through omega n on M1 as arguments. And this we will then define as the tensor T, which was defined on M2, and we're going to have the push forward of all of these vectors V1 through Vm. But the way now to relate the dual vectors to dual vectors on M2 is to take the pullback of the inverse of F. So F inverse star omega 1, and the same thing for the rest. F inverse star omega n. So if you have this this function between the manifolds invertible, then you can relate NM tensors on the two manifolds with each other. Any questions on that? Okay, so the last thing that I want to discuss today is vector fields. And and what is called flows of vector fields, because it's going to be an important concept when we start discussing the definition of derivatives on manifolds. So in Euclidean space, essentially you just have one tangent space. The tangent space is the same everywhere. But in a general manifold, this is not going to be the case. The tangent space in a particular point P is going to be the set of directional derivatives at the point P. So we are going to define now the union of all tangent spaces TPM, and it's going to be called the tangent bundle. Of M. And we denote it just by Tm. And that's then the union of all of the tangent spaces TPM. So an element of the tangent bundle, that's just a vector, a tangent vector in a manifold M at some point P. So in general, an element of Tm here would be a point and the tangent vector at that point. So if we now want to define what a vector field is, a vector field, or if you're a mathematician, you would call this a section of this bundle. That is a mapping, and I'm going to call this V now, from the manifold itself to the tangent bundle, but with an additional constraint. The constraint that if I take this vector field and I evaluate it in the point P, then this vector should be a vector in the tangent space at that point. So each point maps to a vector at that point. That is what we call a vector field. Just as an example, I mean, Euclidean space is also a manifold. I mean, it can be described as we did before, but clearly it's also a manifold based on what we have been discussing here, because there's a rather simple map from Euclidean space to Rn, which is just the identity map. So an example of a vector field would just be if I take a vector and I call it x, and it's equal to x dx plus y dy, with the partial derivatives here understood to be the partial derivatives at the point xy. So this would just be the position vector in Euclidean space. So we would have something like this, and we would have the position vector here, which would look something like this, and so on. So this would be the vector field, and that's the position vector essentially. So each point is associated with a vector at that point, which in Euclidean space happens to be also the vector that translates from the origin to that point. Okay, we have exactly 8 minutes left to discuss the final concepts of today, and that is going to be the flow of a vector field. So given a vector field, I can just draw one vector. Oops. Let me just draw a vector field here. Might look something like this. I can construct a family of curves such that this vector field, which I can call x here, at each point, these curves are going to have the vector field x as its tangent vector. So I can also, so this is a family of curves that looks something like that, right? So for these curves, at each point that they pass through, x is going to be the tangent at that point. So we define the flow of a vector field. So let's call the vector field x. It's a collection of curves that satisfies the following. So let me call it gamma x. So it depends on x, and it's going to be a function from m cross r to m itself. So the real parameter here is going to be the curve parameter, whereas the element of the manifold itself is going to tell us which curve we are on. So for example, I could have a p here and a curve parameter s is going to go along the curve. So what I want is that when I take this p and then I translate with the curve parameter s, x should be the tangent of these curves. And if I choose a different point p, then this would be the tangent. And maps then to something which we can call gamma of ps, gamma x of ps, sorry, which is a point in the manifold. So if I take the point p here and I say I want to follow the flow of x for a parameter value of 2, maybe I end up here, and this then would be the this point here then would be gamma x of p and 2, because it's what I get when I follow the flow of x for a curve parameter value of 2. So the additional requirement then is that I want the following to be true. I want that gamma x of p and 0 should be equal to p. So if I follow the flow for a curve parameter of 0, I should be at the same point where I started. And the second is that if I take the tangent vector, so gamma dot x, and this is the tangent vector then with respect to the curve parameter s, evaluated at p at s and s, that should be the vector field x evaluated at this point, gamma ps. Which means that if you look at the components, so gamma dot x a, this should be the derivative of the coordinates with respect to the curve parameter, which then according to this equality should be equal to the components of the vector field x. So let's take an example here. I think it fits in this box essentially. So let's take the following vector field. We can let x be the vector field x dy minus y dx in Euclidean space. Now, this is essentially, if we draw Euclidean space here, this is essentially a vector field going around like this. So we would expect that the flow lines of this, if we're going to follow this around, should be circles. But let's see how that comes about. So this means, if we look at these two requirements, first of all, that x of 0, or rather x of, if I start at x0 and have curve parameter 0, this should be equal to x0. And the same thing for the y coordinates. Or rather, let's have position vector x0 because it's a point. And the same thing for the y coordinate, this should be the y coordinate at curve parameter 0. And the differential equation here that I need to satisfy is exactly this one. So I would have x dot, which is the x coordinate, should be the x component of this vector field, which is minus y. So we will have x dot equal to minus y. And for the y dot, that should be equal to the y component of this vector field x, which is x. And now if you plug one into the other, you will end up with x, take the derivative, x double dot is minus y dot, which is equal to x to minus x. So this means, which means that x double dot plus x is equal to 0, and you know that this has the solution that x is let's see, x is, well, a constant cosine s plus constant sine s, and differentiating this, you get that this is minus a sine s plus b cosine s, and then identifying with the initial conditions, we would identify that a is equal to x0 and b would be equal to y0. And that then will give you the flow line that starts at x0, y0. And as you can see, it's exactly a circle, as we would expect. So I'm sorry I went 1 minute over now, but I have discussed everything that I want to discuss now, essentially. Just let me say that if you consider, just one more thing, if you consider now the following, so gamma of Sx, so if we multiply the function, the vector field by some value s, then this gamma Sx p of p and 1, that's going to be the same thing as gamma x of p and s. But if we define then gamma s of, because this 1 here is a constant, it doesn't really, it's not really a parameter, we can just write gamma sx of p. This is a function from m to itself. And this is going to be particularly useful when we start defining derivatives.